Assalamualaikum warahmatullahi wabarakatuh and very good day to all of you. Today we're going to learn on a new chapter in CPE501 Chemical Process Control, which is the basic element in process control. Process control for the heat exchanger shown in the slide is identified as temperature controller. It consists of measured element represented by the TT symbol, where process variables measure from the output stream. The signal obtained from the sensor was then transmitted to the second element in the process control, that is decision. Feedback controller or TC symbol in the figure will send the process signal to the third element of process control, that is action. Control valve representing the final control element will take an action based on the signal received from the controller. As mentioned before, basic elements of control system consist of three elements that are measurement, decision, and action. Sensor-transmitter combination will be a representative of measurement component, while the feedback controller will represent the decision component. The common final control element represents the action component in control system is a control valve. As we discussed in previous session, a control loop is a process management system designed to maintain a process variable at the desired set point. Each step in the loop works in conjunction with the others to manage the system. Common process variable control in the chemical process are pressure, level, temperature, and pH. Any deviation from set point will be measured by the sensor and transmitter combination. The sensor and transmitter is the device that conducts the measurements and conversions of variables into analogous or electrical information. The term transducer may be used for a device that converts a signal from one form to another, like for example converting a voltage into a proportional current. The sensor, after measuring the variables, transmits the measurements as electric signal back to the controller. The controller in process control loop is the regulatory part that seeks to keep the measured process variable at a constant as indicated by the transmitter. It also acts an error signal that are generated in the process and determines what control action to take. To determine the control action to be taken, the controller performs an evaluation by either electronic signal processing, pneumatic signal processing, or by a computer function, which is mostly used in industries due to the rapid growth of computer use. The controller requires an input of a representation of the set point, that is the reference value of the variable, and the measured indication of the control variable, both expressed in equal terms as the measured value. The final evaluation details determining the action needed to make the controller value same as the set point. Finally, the final control element, that is a control valve, implements the real-life solution taken by the controller by taking in input signal and transforming them into equal partitions of equation operation performed in the process. It performs the required changes in the control variable to make them equal to the set point. If any changes ever occur again, then the loop starts again. Measurement, as I mentioned earlier, consists of sensor-transmitter combination. The aim is to measure the deviation and transmit the information to the controller. The general configuration of a measurement typically consists of a sensing element combined with a driving element, which is a transmitter. It generates a signal transmitter output, which is related to the process variable. Ideally, the relationship of transmitter output and process variable is linear. The transmitter output is proportional to the process variable, as can be seen in figure on the top. However, the relationship of process variables and transmitter output can be nonlinear. The example can be seen in thermocouples and orifice flow meter. The example of nonlinear relationship can be seen in the figure below. There are three important terms that you need to know in sensor-transmitter combination. The first term is range. What is range? Range is the low and high value of the variable that is measured. Consider a pressure sensor transmitter that has been calibrated to measure process pressure between the value of 20 psig and 50 psig. So what is the range of these sensor transmitter combinations? The range of this sensor transmitter combination is in between 20 and 50 psig. Next, the term span. What is the span? Span is the difference between high and low value of the range. So, from the figure, what is the span for this sensor transmitter combination? The span is 50 minus 20, which is the 30 psi. The final terms that you need to know in sensor transmitter combination is 0. What is 0? 0 is low value of the range. It's often referred to as the zero of the instrument. So, from figure, what is the 0 for these sensor transmitter combinations? Yes, the 0 is at 20 psig. From the figure, can you identify gain for the transmitter? What is 0 with refer to this figure, and what is the span for each transmitter? Later, we will learn how to identify the gain for the transmitter. So for now, we will identify what is the 0 and also the span for the transmitter. Based on previous slide definition, the range is in between 0 to 200 psig. You can see the x-axis from the graph. So the 0 is the low value of the range, that is 0 psig, and the span is the difference between high and low value of the range, that is 200 minus 0, which is 200 psig. Every process variable requires its own transmitter instrument. The table shows some of the examples of the transmitter for each process variable. For example, online measurement option for temperature is thermocouple resistant temperature detector. For flow, orifice venturi rotameter turbine ultrasonic magnetic is the instrument for transmitter. Whereas for pressure, the example of transmitter is liquid column, elastic element, strain gauge, and etc. For the level transmitter, the example of the transmitter is radar, float activated, so on and so forth. And also for the combination, the example of transmitter is gas liquid chromatography, mass spectrophotometer, and etc. The main objective of the sensor-transmitter combination is to measure process variable and then to convert it into the transmitter signal to the controller and send it to the controller. So, in order to do that, we need to identify the transfer function of the transmitter. The transfer function of the sensor-transmitter combination relates to its output signal to its input, which is a process variable as shown in the slide. The simplest form of the transfer function is a first-order lag as represented in equation 1. The numerator is present for electrical signal while the denominator is present the change in process variable. The transmitter gain is the change in electrical signal divided by the change in the process variable and identified as kT, and tau t is referring to the transmitter time constant. When the relationship between the transmitter output and the process variable is linear, the transmitter gain is simple to obtain once the span is known. Consider an electronic pressure transmitter with a range of 0 to 200 psig as shown in the figure. It represents for the x-axis, which is the measured process variable, whereas y-axis represents the electronic signal from the transmitter, whether it is in electronic signal in the range 4 to 20 mA or in the transmitter output percentage, which is in between 0 to 100. So transmitter gain can be obtained in two different units. For the current electronic signal, transmitter gain can be obtained by dividing the output, which is the electronic signal range from 20 minus 4, divided by the range of the process variable, which is 200 minus 0. So we will get 0.08 mA over psig. Or in percent transmitter output or percent TO, you will divide the output to the input. The output in percent transmitter output, the range is in between 0 to 100, divided by the x-axis, which is the measured process variable, between 200 minus 0. You will get 0.5% TO over psig. Again, of a sensor transmitter is the ratio of the span of the output signal to the span of the variable. While the linear relationship of the signals transmitter combination is easy to establish, for a non-linear instrument, the gain can be obtained from any particular operating point, which is the tangent to the characteristic input to the output relation at the operating point. By now, I'm sure all of you can relate to important terms in sensor transmitter combination, which is the span, range, and also zero. So with those information, you need to apply in order to calculate the gain of the transmitter. Try to solve question 1, which is divided into two subsection. You need to calculate the gain in percent transmitter output, percent TO per variable unit, and current output per variable unit. In order to solve this kind of problem, you need to know the range for percent transmitter output. The percent transmitter output range is in between 0 to 100, whereas for current output per variable unit, the range for current output is in between 4 mA to 20 mA. And then you need to write the transfer function and draw the block diagram. So refresh back to the transfer function calculation. So the transfer function calculation for sensor transmitter combination, you need to relate in between the output, which is the signal, electric signal or percent transmitter signal from the transmitter, divided by the input, which is the measured process variable. So you need to solve for these two events, which is the first one, a temperature transmitter with a range of 100 to 350 degree Fahrenheit and a time constant of 30 seconds. And also the second question is a pressure transmitter with a range of 0 to 50 psig and a time constant of 3 seconds. I'll show you how to solve the example for question 1.1 and for you to complete it for 1.2. Question 1.2. For condition question 1.1, the condition is a temperature transmitter with a range of 100 to 350 degree Fahrenheit and a time constant of 30 seconds. You need to calculate the gain in percent transmitter output, which is the percent TO per variable unit, and also gain in current output per variable unit. In order to solve gain for percent transmitter output, remember the range for percent transmitter output. As I said earlier, the range is in between 100 to 0 and 100. So 100 minus 0 divide by x-axis. Your x-axis is in between 350 minus 100. It has been stated in the question. So you will get the gain for percent transmitter output, which is the 0.4% TO over degree Fahrenheit. For the gain in current output per variable unit, you must remember the range. The range is in between 4 to 20 mA output. So to solve this question, you need to divide the output by its input. The output is the current transmitter, which is 20 minus 4 divided by 350 minus 100 degree Fahrenheit. You will get the gain for current output per variable unit equal to 0.064 milliampere per degree Fahrenheit. Now you need to solve in order to find the transmitter transfer function. So this is the equation in order to solve the transmitter transfer function, which is represented by this equation. Hs equals to Kt, which is the transmitter gain, divided by tau s plus 1. So you have been calculate the transmitter gain and just plug in into the equation, then you will get the transfer function. The transfer function for question number 1 is 0.064 divided by 30s plus 1. Then I'll show you how to draw a block diagram, and please solve for question number 2 and block diagram for a temperature controller shows in the bottom figure in the slide. Transmitter function located at the bottom loop where the signal received in degree Fahrenheit, and transmitter output transfer in current signal, that is milliampere, MA. The third figure shows in the slide is the drawing of temperature controller in PNID diagram. TT symbol represents sensor transmitter combination, receive signal in degree Fahrenheit and transmit signal in electronic signal, which is in MA, to the TC represent the temperature controller transfer signal to control valve in PSIG unit. The figure shows the general process control loop for feedback controller. All elements that should be available in process control loop can be clearly seen here. The sensor transmitter combination, the controller, the set point, the process variable, and also the process disturbance. Now, we will try to solve question number 2. A temperature transmitter with a range of 100 to 350 degree Fahrenheit. If the measured temperature in the outlet flow is 200 degree Fahrenheit, calculate A, the current signal transmitted to the controller, B, the percent signal transmitted to the controller. To solve question 2A, you need to do an interpolation at the measured temperature. So the current signal transmitted to the controller at 200 degree Fahrenheit. So you know the minimum range of the current signal is 4, while the maximum range for the current signal is 20. Whereas the range of the temperature is in between 100 degree Fahrenheit and also 350 degree Fahrenheit. So you need to do an interpolation, and after you do the interpolation, you will get the answer of the current signal transmitted to the controller at 200 degree Fahrenheit is equals to 10.4 milliampere. So try to solve for percent signal in percent TO. As a conclusion, besides you need to know what is the process span, what is the range, and what is the zero for sensor transmitter combination. You also need to memorize the signal, which is it can be in pneumatic transmitter. You must remember this range in between 3 to 15 psi. In an electronic signal, which is in current transmitter, which is the range is in between 4 to 20 milliampere output. And finally, the voltage transmitter range, which is in between 1 to 5 volt or VDC unit. So that's all for today. Thank you. Assalamualaikum warahmatullahi wabarakatuh.